In this video, I will show you how to integrate using inverse trig functions. In previous videos, we have solved similar looking integrals using natural logs. So what about this problem lets us know that we need to use inverse trig integrals instead? It's all about the degree. Notice that the degree of the numerator is 0, while the degree of the denominator is 2. If the degree of the denominator is 1 more than the numerator, then it's probably going to be a natural log problem. If the degree of the denominator is 2 or more greater than the numerator, that's how you know it's going to probably be an inverse trig function. Here are the 3 inverse trig integrals that you will need to memorize. So first we need to decide which situation we're in. In problem number 4, there is no square root in the denominator and we see the plus. So that means we are probably talking about arctangent. To make it fit properly, we need to get parentheses in here. This will be our u in a moment. So notice that the quantity 3x squared is the same as 9x squared. If I square the 3 and I square the x, that takes me right back to 9x squared. But in this form, I can say that u will equal 3x. We will also need u prime, which is 3. But we also need to know what a is. In this case, we just have a 1. So that's the same as 1 squared. So guess what? A is 1. Let's go ahead and do the substitution. So we have 12 over 1 plus u squared. Instead of dx, we will write du divided by u prime, which is 3. 3 goes into 12 4 times, and let's put that 4 out in the front. Now we have a perfect match for the formula. So let's go ahead and use the memorized rule. We have 1 over a, but a is 1, so we don't need to write anything here. Let's go ahead and write arctangent, and then we have u over a. Again, a is 1, so that'll just be u plus c. Don't forget that we had this 4 in the front, so I am going to bring that down. Substituting 3x back in for u, and we have the final answer. For number 8, which one of these inverse trig integrals do you think we're probably going to use? It's looking like arcsecant, right? We have the square root in there. We also have this extra x out in the front, just like we have this u right here. And we have the constant is second. We have the variable minus the constant. And that's the order that we have for the arcsecant integral. So this is probably the one to shoot for. To make it a more perfect match, notice that we have u squared in the formula. So instead of x to the 4th power, let's write this as x squared squared so that we have a u squared. Speaking of u, let's let u equal x squared, which means that u prime will equal 2x. Looking at the 4, we can also say that a is 2. We need a squared, and 4 is 2 squared, so a is 2. Essentially, a will always be the square root of whatever we see here, so the square root of 4 is 2, so you know that a is 2. Let's go ahead and make this substitution and see what happens. So for now we have x and then the square root. We will have u squared. U is x squared, and there it is. So we have u squared minus 4. Instead of writing dx, we will write du over u prime, which is 2x. The 2 in the denominator can be brought out front as a 1/2. Then I have x times x, so I get x squared. For a split second, I'm concerned because I still have x's, and I only want u's. That's until I remember that u is equal to x squared. So we can easily replace this x squared with a u. This is now a perfect match for the formula. So we can go ahead and use this memorized rule. So we need to have 1 over a, and remember that a is 2. So I'm going to say 1 over 2, and then arcsecant. Arcsecant is the only one that has the absolute value around the u over a. And then we will go ahead and put u over a, so u over 2 plus c. Don't forget that we have this extra 1/2 that's in the front. The 1/2 that I'm writing here is the 1 over a in the formula. That is separate from the 1/2 that's already sitting here. So I'm going to have 1/2 times 1/2. So of course for the final answer I will actually have 1/4 arcsecant, and u was x squared. So I have x squared over 2 plus c. So that's the final answer. Which rule do you think we will use for number 12? It's looking a lot like arcsecant again. To make it a better match, let's rewrite 9x squared as the quantity 3x squared. That tells us that the u must be 3x, which of course means that u prime is 3. We also need to know what the a value is, and looking at the 25, we know that the a is 5. It's always going to be the square root of this number. Substituting u for 3x, we have this. Of course, instead of writing dx, we will now write du divided by u prime, which is 3. I am momentarily concerned because we still have this x sitting here. I don't want any x's, I want only u's. So what do? Well, I realize that u is equal to 3x. If I solve this little equation for x, then I have x is equal to u over 3, which I will view as x equals 1/3 u. So if I want to replace this x with an expression involving u, I can erase the x and put 1/3 u in its place. Alright, that's better. Now we have all u's. And as an added bonus, I see that we have 1/3 times 3. So these will cancel each other out. On the next step, I'm going to take this 2 and put it outside of the integral sign. As you can see, this is a perfect match for the memorized rule. So let's go ahead and do it. We have 1 over a, so that's going to be 1 over 5, times the arcsecant, absolute value of u over a, so u over 5, plus c. Don't forget about the 2 that's in the front as well. Substituting 3x back in for u, we have the final answer. Now, which one of these rules do you think we will use for problem number 16? I'm betting it's going to turn out to be the first one because of the plus. We have this plus right here, and this is the only rule that has a plus in it. Also, even though there's a little radical x here, there's no square root over the 1 plus x, and this is the one rule that doesn't have a big old square root across the denominator. So all signs point to arctangent. If I'm going to use this rule, I need something squared right here. Instead of just a plain x, I need to rewrite this somehow as something squared. So how can I rewrite x as something squared? Well, if I had x to the 1/2 power, and then I squared it, wouldn't that be the same thing as x? Because when you raise a power to a power, you multiply. And if you multiply 1/2 times 2, then you get 1. So these are actually the same thing. So on the next step, I'm going to replace x with x to the 1/2 power squared. That way I will have something squared. Now I can see that u must be x to the 1/2 power. So u is equal to x to the 1/2 power, which means that u prime is going to equal 1/2 x to the negative 1/2 power. A must be 1 because I just see the 1 right there. So A is 1. So far, I went ahead and substituted u for x to the 1/2 power, so I have u squared. I also rewrote the square root of x as x to the 1/2 power to make it more obvious what's about to happen next. Instead of dx, I will write du divided by u prime, which is 1/2 x to the negative 1/2 power. So here we go, 1/2 x to the negative 1/2 power. So this is what I was hoping would be obvious. If I multiply x to the negative 1/2 power times x to the positive 1/2 power, these are going to cancel each other out. This would be x to the 0 power. This makes 1. So these are now gone. Similarly, 2 times 1/2 also makes 1. So these also cancel each other out. I went ahead and took the 3 from the numerator and put it right out in the front of the integral. So as you can see, we have a perfect match for the rule. So let's go ahead and do it. So we have 1 over a, but we decided that a would equal 1. So I don't really even need to write that because that's 1 over 1. So I will move on to the arctangent of u over a. So that's really just u plus c. Don't forget about the 3 that's in the very front though. So there it is. Substituting x to the 1/2 power back in for u. And in fact, I think I'll go ahead and write it as the square root. It's just a little tidier. It doesn't really matter. But we will have 3 times arctangent square root of x plus c. Amazing.